Hello, everybody, and welcome to another wonderful day of physical chemistry. So today we're going to be focusing in on rotational selection rules. So a way to think about this is going to be taking what we talked about last time with rotational energies and now overlaying it with a little bit of group theory. So, in order to actually interpret a rotational spectra, the first thing we need to figure out is which photon absorption events are actually going to be possible. Because it turns out not every photon will be equally absorbed by a molecule. Because remember, we need to first establish which selections will actually be possible using our good old friend, the transition dipole moment. So photon comes in with uh, with an oscillating electric field, and I need to have that oscillation match up with the difference in between my initials and final states. So the first thing we're going to want to try and establish is a gross selection rule. So this is going to simply be which molecules can undergo rotational excitation. So because a photon is a oscillating electromagnetic field, it can only interact with the system where I see a change in the oscillation of the magnetic field. So a good way to think about this is I have a nice polar linear molecule, and the photon comes in with its oscillating electric field. So when it's absorbed by the molecule has to end up taking up that oscillation. If the molecule was already rotating, then it can either slow it can either start rotating in the opposite direction, or more likely, since energy is coming in and that energy also needs to be spent for an absorption event, it will end up speeding up. So in practice, in order for this molecule to have a uh, electric field to interact with, it needs to have what's called a permanent dipole moment. So this is another fancy way of saying a permanent positive end and a negative end, more commonly known as it has to be polar. So now that we've first identified that a molecule has to be polar in order to interact with the photon, we have to figure out what specific selection rules, which is another fancy way of saying what are the possible end states for this excitation. We know it can occur. What will it end up looking like? So since our photon is going to bring in an angular momentum of 1, this means that I have to have a change in the angular momentum of the molecule of +1 if I'm undergoing an excitation. So this means my energy is going up, or a relaxation in a relaxation event, such as the molecule losing energy, I can also see a decrease in the angular momentum for 1. However, in practice for photonic absorption, we're only going to see an increase in the value of J. However, we will encounter some systems, such as coupled excitations, where I can have a relaxation of the rotational motion as well. However, we still need to figure out what this is going to mean um, for directional movement. Now, the important thing is that we don't really have any net dependence upon an external reference or z-axis. So as a consequence, our m sub j could increase, it could decrease, or it could stay the same. So for example, if the molecule is already pointed up and it absorbs a photon to increase its speed pointing up, that would be a +1. If the molecule is stationary and then absorbs a photon going in the counterclockwise method, we'll have a decrease in the angular momentum in the z-axis. Or the photon could come in a completely different direction, like the x or y plane, which result in no change of the magnetic moment. However, one of the things that we should acknowledge is that when I start dealing with nonlinear molecules and I have a k dependency, which again is going to be the rotation about the principal axis, my change in k actually has to be 0. And the reason why is for a symmetric molecule, I will have no dipole along this principal axis. So you can imagine this system for a polyatomic system where I've got largely symmetric systems out here. That doesn't so much matter because the dipole is entirely located along that principal axis. And as a result, any change in motion in another direction can be essentially considered nonpolar. And as such, it falls victim to our selection rules. So these transitions aren't going to be possible. So now using these selection rules and our knowledge from last time, we can figure out an energy for a rotational absorption event. So we can do this by simply taking the difference of our J values. So our ending J plus 1 minus our initial J, which is J, we substitute in our rotational constant. And when we simplify the system, we find out that the change in our vibration, in our rotational terms, so essentially the rotational energy of the system, will be twice our rotational constant times our initial starting quantum number plus 1. As a consequence, what this means is that our energies will tend to separate out the larger and larger my initial J value. So initially quite close together and increasingly further and further apart. However, we can also try and extend this to a symmetric molecule. However, since K is equal to 0, well, it means that it's going to end up the addition of K terms on the end of these expressions really won't matter since they will end up canceling out. And as a result, despite a much more complex energy structure, a symmetric molecule will actually contain an identical energy spectra, which can be actually fairly useful. Now, using these phenomena, we can actually predict a real microwave spectra, which can be a little bit more complicated than you might imagine. So one of the reasons why is that rotational spectra have multiple peaks because our absorption energies essentially keep increasing with J values. So each J value will have its own unique peak. Now, one of the cool features of this, though, is that these peaks have a pretty uniform separation. Because when I take the difference in between J of 0 and 1, well, the difference is twice the rotational constant. J1 and 2, well, the difference is twice the rotational constant. And that's actually going to be true for any of our peaks. So this is often referred to as line spacing. And if I'm able to get a specific set of, I'm able to get the line spacing or average line spacing for a spectra, it should have a fairly consistent value of twice the rotational constant, which can then be used to essentially calculate the moment of inertia in the perpendicular axis. Note that we do get no information about parallel axes from this rotational spectroscopy. However, one of the things to make note of is if I've got a more complex system, like a symmetric system, we might have to use multiple isotopes to determine all of the various bond distances present, because many different bond distances can go into calculating a single moment of inertia. So that is worth noting. One of the other features that is also worth acknowledging is that for high J values, we can also have centrifugal distortion, which can start to bring together our large J value peaks. As I have faster rotation, my bond essentially will start spreading out and getting larger moments of inertia. So that is worth noting if you do see deviation at large frequencies or J values, to watch out for the centrifugal distortion. However, one of the things that you may note about the spectra is that, well, it's a little bit odd in its shape. Now, one of the reasons why its shape is a little bit odd is that it turns out that not only does our energy and our energy spacing increase with J value, so does our degeneracy. So again, for a linear system, my ground state is singly degenerate, my first excited state is triply quintuply, and so on and so forth, with increasing J values as I go up. Now, this means that according to statistical mechanics, I'm going to see an increase in the population of my rotational states as I go up in J values till essentially the energy difference overwhelms the increase in degeneracy. So in practice, we tend to find that the most commonly occupied rotational states are those with an intermediate J value. Now, trying to determine which one of these J values is going to be the most common and consequently should have the largest intensity, we need to, well, use a little bit of statistical mechanics. So using that, we can simplify an equation to derive the rotational state with the maximum occupancy as being based on essentially the temperature of the system and the rotational constant, or again, energy spacing. So one of the things to make note of, higher energy spacing, the more likely that I'm going to populate a lower rotational state. Higher temperature, again, more energy to occupy those excited states, the more likely I am to occupy high energy J states with their larger degeneracies. However, it is worth noting that this energy system, this system with its degenerate energy levels can actually be broken down a little bit under real world circumstances. One of the more common circumstances exhibits what's called the Stark effect. No, this has nothing to do with Iron Man. It's essentially just based on the idea that if I apply an electric field to my system, I can essentially start separating out my energy levels based on the magnetic moment. And again, this should kind of make sense because, again, magnetic moment tells me how much of my magnetic field is pointed in the Z direction. Now, by definition, any electric field that I apply is going to be along the Z axis because that is an artificial choice. So as a result, what we tend to see is that for large M sub J values, this means I have a large magnetic moment or electric field pointed in this Z axis. And for an electric field, it doesn't matter whether the motion is forwards or backwards. Either one will align with the electric field. And so what we find is that as M sub J values get greater, I'm going to tend to favor large magnitude M sub J. So whether, again, positive or negative. And I'm going to disfavor the magnetic moment being pointed in the XY plane, so values of 0 for M sub J. And so this lets me split out my system based on the based on its magnetic field. Now, this can be a very useful way in analyzing these degenerate terms, and especially its use comes in when we're actually trying to look at our dipole moment, or essentially how polar the molecule is. Because the more polar the molecule is, the more oscillating charge I have, and the more susceptible it will be to the application of electric field. So in application, we could examine the Stark effect by applying a large magnetic field, then using photonic absorption to measure the system. And what we should see is a splitting of our spectra based on how much the Stark effect splits up these M sub J values. It generates a much more complicated microwave spectra, but is highly useful in examining the polarity of certain molecules. So that brings us to the end of looking at rotational absorption events. Next time, we're going to dig a little bit more into rotational Raman. And no, it has nothing to do with the suit. Till then, take care.